Hi everyone, my name is Sarah Skorpen. I am a senior lecturer at the University of Pretoria in the Civil Engineering Department and in the Engineering Faculty, EBIT faculty. I am a structural engineer. I studied civil engineering at the University of Pretoria, and then I have worked for almost 10 years specifically in the field of structural engineering before coming back to the university and continue with postgraduate studies, and eventually got my PhD and have been lecturing whilst doing postgraduate studies. Structural engineering is part of civil engineering, and it's basically dealing with the design, the analysis and design of structures. And so when you're talking about structures, you're talking about buildings and bridges and infrastructure like dam walls, etc. That's probably more linked to hydraulic structures, but structural engineers get involved in dam structures. So that's kind of what a structural engineer is doing, is designing those structures. Basically, when we say designing, it means sizing the elements. So often we think about architects being involved with buildings, and they are very part of building process, but they will be, say, designing the functionality of the building and what it looks like. And structural engineer needs to make sure the sizes of the columns are correct, thickness of the slabs, etc. If you're looking at structural engineering, typically most people would be looking at the design of concrete, reinforced concrete structures or structural steel structures. I'm lecturing, focusing on structural steel structures, but we also have a big component of our undergraduate subjects which look at reinforced concrete. In terms of my research, I have focused on bridge structures, and that's something I've really always had an interest in. And just whenever I drive over an interesting bridge, I really enjoy it. Or if I'm watching a movie, I often just look out for the interesting structures, the interesting printers. They always catch my eye. So it's something I've always had an interest in, and I've been really fortunate to be able to do research on integral bridges. And that's something that's kind of new to the bridge world, where the deck of the bridge, which is what you drive on, is tied into cast monolithically. So it's fixed to the abutment, which is basically a retaining wall at the end of the bridge. And that leads to a much more economical structure in terms of maintenance, because you don't have bearings and expansion joints, which need to be maintained every few years. So from a client's perspective, a client like Sanral or as a municipality, that's much less maintenance. So that's why it's quite an exciting sort of semi-new field in bridges, and in the last 10, 15 years, it's really gaining momentum. A lot of clients are really insisting on whichever structures can be made integral to make it. But from a design point of view, it's a lot trickier to design for a structural engineer. So we've looked at monitoring the longest integral bridge in South Africa to date, and looked at the behaviour of that bridge. We've been able to measure the movement and the temperature and the structure, the shrinkage of the structure, because it's concrete structure. And we've been able to provide some answers to engineers to how these bridges actually behave, what's critical to look at, etc. So that was a really exciting project. It's quite an old project now. It's 10 years old, and you've been monitoring this bridge. It's in the Free State. It's called the Van Sailspruit Bridge, and we've been monitoring temperature, movement, strain. Strain is basically what we can change in length over original length, if you think back to just basic physics. So we can't measure stress in structures, we can measure strain. And that helps us to understand what's happening in the concrete, the reinforced concrete deck. We've been monitoring earth pressure behind the abutment walls, with the retaining walls. And it's been really interesting to see how seasonally the bridge behaves and changes, between the difference between summer and winter, and what's happening autumn and spring, and to be able to understand integral bridges better and help us to design more economical structures from the client's perspective. It helped the designer, because it's a more complex design, to be more economical in terms of their design method as well. And that's led to other projects. So that is kind of was our first bridge that we've been monitoring. And now they've actually got quite a few other projects, structural health monitoring projects, not just with looking at interval bridges, but also other types of bridge construction. At the moment, we're monitoring 2 bridges in Durban, and both interval bridges. And the one is actually a curved interval bridge. So really interesting to look at how the curved structure now forms being tied into the ends, the beer butt walls at the ends. So that's quite an exciting project that we're looking at with eThekwini municipality. It's also in a different environment compared to the bridge in the Free State. So that's also interesting to see how the humidity, the moisture content air actually affects these structures. Because it's interesting that, actually the environment is one of the loads that you have to consider on bridge. It's not just the tracks driving over it, etc. So that's quite exciting. You'll be looking at an and incremental launch bridge and helping a consulting engineer look at instrumenting that during construction, because when you're designing a bridge, you are not just thinking about the final condition of the trucks driving over it, but also how is it going to be constructed, and you've got to make sure that it's the structure is able to withstand all the loads during construction. So and then being able to monitor a structure during construction is helpful to understand what's happening, especially if it's a fairly complex construction process. And depending on where the bridge is built, the construction process could actually be the critical load case for a bridge design. We've got a new project coming up in Limpopo now. We also are looking at a post-tension deck and monitoring how that is going to deform. So that's a new project in the pipeline, and that's quite exciting to look at. Post-tensioning is where you stress the concrete, so you take out the tension on the concrete, so you can go for longer spans, longer lengths of between piers and between the columns, and so that's also now going to be interesting to see how post-tensioned interval bridge is going to behave, and be quite excited about that project. So if we're talking about monitoring a structure, or call it structural health monitoring, what is that? And what we've done on the bridge that I did my PhD on in the Free State is we've embedded sensors into the concrete. So what do those sensors do? Well, they measure things like temperature. They measure strain, a change in length over original length is calculated strain. And they can measure earth pressure with sensors. You can measure moisture content with sensors. So these are all sensors that would be embedded in the structure. Sometimes you can stick sensors onto the side of a structure so we can measure again that strain and temperature. We can also put tilt sensors into a structure to measure movement. If we've got a point that we know is not moving, we could calculate displacement relative to that rate. And that's something we've done on the interval bridges so that we can measure the movement of the top of that retaining wall, the abutment wall at the end of the bridge. Because that's obviously going to be important to know how is that affecting the road, service, deck stewards, etc. So those are all things that we can measure, and then from that we can now analyze and look at how the structure is behaving and look at what the load effects are on the structure from that movement or that change in temperature, etc. And we can understand how the structure is working and understand what we have to design the structure to withstand in terms of environmental events. We can also obviously measure the load on the structure in terms of a load test. So that's something we've also done on structures, looked at what is the load from a truck, where is that truck placed, and then looked at how does that, what is the effect of that truck at that position on the structure, and how does it relate back to how we design it. We can do something like a load test, and that's done. So that's kind of what structural health monitoring is looking like. You can also, and in terms of structural health monitoring, you need to look at obviously embedding the sensor in to measure what you want to measure, like temperature or strain or tilt, and then you've got to actually log that measurement. So we use loggers to do that and get the data basically from the sensor. And then you need to know what you want to be measuring. So if we're looking at truck load and dynamic load, that's a dynamic load on the structure. If it's driving over the structure, then we want to be logging it we want to taking measurements very, very quick. But if we're looking at just environmental effects like change in temperature or change in moisture content, then we don't need to be measuring it that quickly. So they'll be logging it at lower speed. So that's something we're looking at. We obviously need to decide, what are we focusing on? Are we focusing on dynamic effects, or are we focusing on something that is very slowly changing with time, and that will affect how we take the measurements and how we program the loggers, etc. And then we get that data from the loggers. This is typically done totally remotely. So these are all in remote sites. So we don't go and download the data. We've got a SIG up there that we could remotely access for data. And then we download that to a central server, basically, and then we can access the data and then look at the data. And that's really what we are doing at the university, is looking at that data and interpreting it and saying what is actually happening to the structure. If we change something, would the structure behave differently, etc. Analyzing that to gain my sort of, not dream, but my goal is to try and help structural engineers understand structures better. And if we can do that by analyzing the data and plotting trends, noticing trends, etc., and just helping us understand structures better. If we can understand structures better, we can design more cost-effective structures. So that's basically, in a nutshell, what we're trying to do with structured health monitoring. So in terms of analyzing data, that often is done with what postgraduates do. It's often part of that process, a very integral part of that process, because they are typically either doing a master's or a PhD and have got a lot of time set aside just to look at one aspect of a project. So we've got a lot of master students, some PhD students working on these projects, and they're obviously going to be focusing on one aspect of that, and then really zooming into that, analyzing that data, making comparisons, etc. And obviously part of their studies is going to be coming up with some conclusions as to what's happening in the structure. How could we have done this differently, or stuff like that. The other really important thing with structures is to understand the materials, and this is also one thing I really enjoy about structures, is just see the interdisciplinary sort of stuff that goes on in terms of the structural behavior, the material behavior. So we need to work with the materials engineers, which is also part of civil engineering, to understand that how the concrete materials also influence the structure, or if it's steel structure, how the steel properties influence the behavior of the structure. And on bridges, it goes beyond that, because it's also, now, how does this structure interact with the soil? So that's linking to the soil mechanics and the soil structure interaction. And it's also interdisciplinary in terms of, this has got to carry a road. So these are certain geometric alignment, and that's integral to how the structure behaves. And if it's over a river, then you've got to make sure in terms of the design, it's at the right level. So that's up to the hydraulics engineer or the hydraulic designer to be looking at the flood lines, that you can put the road or the bridge at the right level. So it's so interdisciplinary, and we all are critical in terms of the design. So that's, to me, is a really something really nice about structures, is that I can see how all the disciplines are really needed in the big project scheme of things. And in terms of data analysis, we have been really fortunate to on specifically the bridge that I did my PhD on. We have worked with Cambridge University in terms of putting different sensors on the structure. We were very fortunate to get some funding to put some fiber optics onto that bridge, the Van Salisbury Bridge. And that's another way of measuring strain using fiber optics. And that's used in a lot of different contexts, and a lot of different types of monitoring and fiber optics. And then also with Cambridge, we have been looking at the earth pressures in kilometer detail. We had an exchange program with one of the PhD students, and we've been able to make some, I think, valuable contributions in terms of earth pressure behind integral bridges, because that's something that actually changes seasonally as the deck contracts during winter. It actually pulls away from the soil level, earth pressure decreases, and then in summer the entire structure expands and pushes into the fill, and that increases it. So we've been able to monitor that over a number of seasons and seen how it's changed or not changed at less than we thought, and that's been really quite a nice project, and we've been able to link up with Cambridge of that side. With this project, it's been really exciting to link up with Cambridge University, and specifically we've been looking at the earth pressure over time and with them, and we were able to have a sort of collaborative study with one of their PhD students who came out here, and we together have been looking at the earth pressure data over time, and we were really able to get some good conclusions in terms of what's happening on a fairly long integral bridge. I think I didn't mention that the integral bridge that we were looking at is 90 meters long. And that actually is quite long for an integral bridge. When they were first building it, at that time, the limit on certain countries for integral bridges was only 60 meters. So we were really pushing the bounds of the length of an integral bridge. We've got some good data and have been able to make some valuable contributions together with Cambridge on what is happening in terms of earth pressure behind the abutment as it pulls in the winter, pulls the wall, the abutment wall in as the deck cools, and then in summer expands, it pushes into the fill, and then you get an increased earth pressure. And that obviously is happening seasonally every time it goes from winter into summer. So that's been really interesting to look at it there and help, again, structural engineers and geotechnical engineers understand these structures better. Something that we really are excited about in terms of our structural health monitoring of bridges is basically building up a database of structures that we are going to continue monitoring. So the bridge that I did my PhD on, we've been monitoring for the last 10 years, and currently got a PhD student who is looking at the long-term behavior and looking at trends in what the climates, are there any climate trends that we pick up over the last 10 years? And we're hoping that all our structures that we are now going to be monitoring and have started monitoring, we'll be going to be able to continue to monitor for the foreseeable future. So we can build up a database on what is happening to bridges in South Africa in different environments. It's quite important to see over time is there any effect of climate change that we can understand this better. As well as the other important thing for bridges in terms of structural health monitoring is maintenance of structures as well as a lifespan of structures. Bridges are designed for a certain lifespan, and the question is, well, once they get to the end of that lifespan, what happens to the structure? How much can you keep? How long can you keep using it, basically? So that if you've got some sensors embedded into it, that makes the decision, helps to make those decisions in terms of what needs to be done to prolong the life of the structure. So that's something that we really are quite excited about in terms of structural health monitoring, and where we see it's really helping the end user and the clients to again have structures that can last longer, perform better, etc. In terms of where structural engineers work, I think most of the time a structural engineer is going to work for a consulting engineering company because they would be looking at the design of structures, whether it's buildings or bridges. And that's pretty much where most structural engineers would go. Some structural engineers go to site as well. So obviously we've got the design part of things and then the construction part of things where the contractors, if you're responsible for that. But most of the time, the structural engineer is going to be on the design side, working for the consulting engineer, doing the design and the structure. But we also need structural engineers on site. Some structural engineers actually focus on the construction side of things and temporary works. So looking at the design of how to get structure safely built. And we also need structural engineers on that side of things. But that's typically where you would be employed. Even under that, though, part of your job could be is becoming more and more needing to understand data. I hope I have given you a little bit of a taste of what structural engineers can do and what we do here in terms of structural engineering at the University of Pretoria. And just open your eyes a little bit to structures around you when you are driving around, driving over bridges or driving past buildings. Just have a look at them and sort of try to imagine how they work. And that's really what we are teaching our undergraduate students, postgraduate students, understand how structures work, to be able to design those structures to stand up and take the loads that are applied to them and to make today matter.